Far beyond the planets, Voyager is still sending a radio signal back toward Earth. The question is, how much longer that old machine can keep answering before one part of the conversation finally fails. The hard part is that talking to Earth is not one thing. It takes power. It takes a working transmitter. It takes an antenna pointed home. It takes old computers that can still format data. It takes commands that cross deep space and a deep space network on Earth, sensitive enough to hear the reply, and the spacecraft can keep moving long after that reply stops. By the end of this video, you will understand what has to keep working for Earth to keep hearing Voyager, why the answer is conditional rather than a clean date, and what kind of failure finally turns an operating spacecraft into a silent object. This is one of those questions that looks like a date from far away and becomes an operating stack when we work through it properly. We are going to follow the conversation itself, the power that keeps it alive, the instruments already being sacrificed, the signal crossing interstellar space, the dishes on Earth, the antenna pointing problem, the delay, the fault recovery, and finally the boundary where a mission becomes silence. If you enjoy thinking through questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. Let's separate what we mean by talking, because this is where the whole question changes shape. The weakest version of contact is a carrier. A carrier is not a sentence from the spacecraft. It is a coherent radio signal, a tone with structure, something the deep space network can lock onto and say, the spacecraft is still there and its radio is still behaving in a way we can recognize. That matters. But it is not the same as a healthy mission. The next layer is engineering telemetry. Telemetry is the spacecraft describing itself. Voltages, temperatures, switch states, computer status, whether a command was accepted. It is not the grand science story people remember from Voyager. It is the health report that tells engineers whether the machine is still controllable. Then there is science data. That is the measurement stream from instruments, magnetic fields, plasma waves, cosmic rays, and whatever part of interstellar space the remaining sensors can still turn into numbers. Science data is why the mission still matters as exploration. But science data can thin out before the spacecraft stops answering. And above all of that sits commandability. Earth has to be able to send instructions and later confirm that Voyager understood them. Without that, a signal can become almost like a lighthouse seen from far away. It may still be visible, but the conversation has changed. So when we ask how long Voyager can keep talking to Earth, we are really asking which of these layers can survive together. Carrier, telemetry, science, command response. They sound like variations of the same word until one of them breaks. Voyager 1 gave us a clean example in 2023 and 2024. The spacecraft was not gone. The radio link had not simply vanished, but the flight data system, the part that prepares information for return to Earth, began sending unusable data. From the outside, that sounds like a simple communications problem. Up close, it was more precise. The spacecraft could still be contacted, but Earth could not read the normal story it was trying to send back. That distinction is the key. A spacecraft can be alive in one layer and unreadable in another. Let's make the distance physical without pretending precision we do not have. Voyager 1 is more than 15 billion miles from Earth, more than 25 billion kilometers. Light itself takes more than 23 hours to cross that gap one way. So if Earth receives a status update on Tuesday night, that status belongs to a spacecraft from almost a day earlier. That sounds like a delay. It is. But for operations, it is more than delay. It means every diagnosis is an old photograph. Every answer is late before it arrives. Engineers are not touching Voyager in real time. They are maintaining a thread of meaning across a gap so large that one round trip takes roughly 2 Earth days. Now put that against the age of the machine. Voyager launched in 1977. That fact is not here for nostalgia. It matters because the electronics, propulsion lines, heaters, computers, and radio system were built for another era. The mission survives because those old systems still overlap with modern ground operations. A weaker version of this story would say Voyager is still alive because NASA can hear it. The better version is narrower. NASA can still maintain a useful exchange with it, as long as enough of the chain remains intact. Let's start with a carrier again. If the Deep Space Network hears a tone, Earth knows something is transmitting. But if telemetry cannot be decoded, engineers may not know what the spacecraft thinks is happening. If telemetry returns but science instruments are off, the spacecraft is responsive but the mission has become less scientifically rich. If science data returns but command ability becomes unreliable, the team may be watching a machine it can no longer confidently steer. These states can overlap. They can also separate. That is why a single final date is such a tempting but misleading answer. It imagines one switch, one last packet, one final message. Voyager is more likely to narrow by layers. One instrument stops, a data mode becomes too limited. A transmitter fallback gives only a thin health stream. A pointing problem reduces margin. A command takes 2 days to test and another week to interpret. The spacecraft can still be there through all of that. The mission conversation is the fragile thing. So the first answer to the title is not a year, it is a definition. Voyager can keep talking to Earth, while Earth can still detect it, understand it, command it, and receive something useful back. The more of those layers remain, the more alive the mission is. The fewer remain, the closer the conversation moves towards silence. And once talking becomes a stack instead of a miracle, the first physical question is simple: what still has enough electricity to stay on? There is another useful way to test the word talking. Ask what Earth could do next. If the DSN hears only a carrier, the next action may be to try to lock the signal, check the frequency, and search for a data mode. If engineering telemetry decodes, the next action becomes more specific. Compare temperatures, voltages, fault flags, and counters against what the team expected. If command confirmation comes back, the mission is still interactive. Those are not philosophical differences. They determine the next engineering move. The 2023 data problem matters because it prevented a lazy answer. Voyager 1 did not simply cross from alive to dead. It entered a strange middle state where the spacecraft was still a target, still a radio source, and still a machine with power, but the meaning was damaged. That is exactly the kind of middle state the final years may contain. The mission can become less readable before it becomes silent. Now notice what the word useful does. A radio trace is useful for reacquisition. Engineering telemetry is useful for diagnosis. Science data is useful for understanding interstellar space. Command acknowledgement is useful for control. Each kind of usefulness belongs to a different audience inside the mission. Navigation, flight operations, science, and long-range planning. When one kind is lost, the entire mission does not instantly vanish, but its purpose shifts. That is also why old documentation and institutional memory matter. When a spacecraft this old behaves strangely, the team is not just checking a dashboard. They are interpreting a machine designed in the 1970s, operated through decades of modifications, with subsystems that may now behave near the edge of their original assumptions. The returned data have to be translated through that history before they become a safe next command. So the first chapter gives us a measuring tool. From this point on, every threat to Voyager is really a threat to one of the communication layers. Power threatens what can remain on. Instruments threaten science return. Radio threatens the data path. Pointing threatens the geometry. Computers threaten meaning. DSN constraints threaten the Earth side. Delay threatens recovery speed. The title question becomes answerable only after all of those layers are visible. There is one more distinction to carry forward before we leave this first layer. A mission can be audible and still be in trouble. We hear that NASA is receiving a signal and the mind fills in a healthy machine. We hear that a signal was interrupted and the mind fills in a dead machine. Neither picture is careful enough. The better mental model is a conversation whose vocabulary keeps shrinking. Early in the mission, Voyager could send pictures, fields, particles, spectra, engineering status, and context around what it was seeing. In the late mission, the vocabulary has narrowed. The machine still speaks, but it speaks in fewer channels, at lower rates, with less redundancy, and with more dependence on ground interpretation. That is not failure. That is age made operational. Think about a telephone line. If you hear a click, you know the line exists. If you hear breathing, you know someone may be there. If you hear broken words, meaning is trying to pass through. If you hear clear sentences, the conversation is strong. Voyager's states are not human states, but the layered logic helps. A carrier is the click. Telemetry is the meaningful phrase. Science data is the detailed answer. Commandability is the ability to ask the next question. Once that structure is clear, every later chapter becomes easier to hear. Power does not simply decide whether Voyager is alive. It decides which layers can keep speaking. Instruments do not simply decide whether Voyager is useful. They decide what kind of answer the spacecraft can still give. The DSN does not simply receive. It determines whether the faintest answer becomes a usable answer. Pointing does not simply orient metal in space. It decides whether the answer is aimed at the listener at all. So when we say Voyager is still answering, we should hear the sentence with pressure inside it. Still answering does not mean comfortably answering. It does not mean fully answering. It means enough of the chain remains aligned for a machine from 1977 to remain part of human operations. That is already extraordinary. Let's follow the what's first, because power is the quiet constraint underneath almost every other Voyager decision. Voyager is not running on a battery in the everyday sense. There is no rechargeable pack slowly draining towards zero while engineers watch a percentage fall. Each spacecraft carries radioisotope thermoelectric generators, usually shortened to RTGs. The plain version is this. Plutonium produces heat as it decays. The spacecraft converts some of that heat into electricity, and the electrical output slowly declines year after year. That decline is steady enough to plan around and serious enough to dominate the mission. NASA and JPL describe the loss as about 4 watts of electrical power each year. 4 watts sounds tiny. It is the scale of a small night light. In a house, you would barely notice it. On Voyager, after almost half a century, 4 watts can be the difference between keeping an instrument alive and shutting it down to protect the spacecraft. That is the reversal. The number is small only if the budget is large. Voyager's budget is not large anymore. Think of the spacecraft as a ledger. On one side, the RTGs still supply power. On the other side, every surviving load asks for some of it. A transmitter needs power, computers need power, heaters need power, attitude control support needs power, science instruments need power, fault protection and voltage regulation have to stay inside safe limits. There is no hidden reserve that lets everything keep running simply because the spacecraft has been heroic so far. This is why instrument shutdowns are not signs that the team has given up. They are often how the team refuses to give up. In April 2026, engineers shut down Voyager 1's Low Energy Charged Particles Experiment, or LECP. That instrument had worked almost continuously since launch. It measured charged particles from the solar system and the galaxy, including particles in the interstellar environment no other human spacecraft has sampled this way. Turning it off was not casual, it was triage. The reason was not just the general decline of power. During a planned roll maneuver in February 2026, Voyager 1's power levels dropped unexpectedly. Engineers were concerned that another drop could trigger undervoltage fault protection. That is an onboard safety response. If the spacecraft thinks demand is too close to supply, it can shut components down on its own to protect itself. Protection sounds comforting until you remember the distance. If Voyager protects itself in a way Earth does not expect, the team has to reconstruct what happened from delayed, limited telemetry. Recovery can become a long, risky process, so the team acted first. They removed a load they had planned to remove eventually. NASA said the shutdown should give Voyager 1 about a year of breathing room, while engineers work on a larger energy-saving reconfiguration. That phrase, breathing room, is useful. It does not mean the mission is safe indefinitely. It means the power ledger has been balanced for a little longer. Let's make the trade plain. If one science instrument uses power, and turning it off keeps the computers, heaters, transmitter, or attitude systems safely inside the margin, then the mission loses one kind of knowledge to preserve the possibility of future knowledge. That is not sentimental. It is arithmetic. There is also heat hidden inside this story. The RTGs produce heat, but not every part of Voyager stays warm just because the power source is warm. The spacecraft has heaters, fuel lines, electronics and old materials that have to remain within tolerable ranges. Engineers have already turned off heaters and non-essential systems across the long mission. That saves electricity, but it asks the hardware to keep working in colder conditions than originally preferred. So power is not only about whether a device has electricity, it is about whether the entire machine remains physically hospitable to itself. This is where the battery metaphor breaks. A phone runs down and stops being useful. Voyager is being deliberately simplified. Loads are removed. Some capabilities disappear. Others are preserved. Each year, the remaining system has to be made slightly smaller without breaking the ability to answer Earth. The annual 4-watt decline also compounds in a brutal way. 1 year may be absorbed by turning off a heater, another by ending an instrument, another by changing how power is routed. But after enough years, the choices become less about comfort and more about core identity. What is the minimum powered spacecraft that can still be called a mission? It needs a transmitter, or at least a usable communication path. It needs computers able to accept commands and format a reply. It needs enough thermal margin that fuel lines and electronics do not cross a fatal boundary. It needs attitude control to keep the high-gain antenna pointed home. It needs protection routines that do not accidentally silence the very systems they are trying to save. Power touches all of them. This is why the end is not distance alone. Voyager is not simply getting farther away until the signal becomes impossible. It is getting farther away while its electrical budget shrinks and its hardware ages. The distance makes the signal faint. The power decline decides what can still be sent, and every time an instrument is turned off, the spacecraft becomes more focused. Less like a fully equipped explorer, more like a careful survivor, using remaining electricity to keep the conversation alive. So the next question follows naturally. If power is the ledger, what gets crossed off that ledger before the ability to speak is sacrificed? The power budget also explains why tiny loads receive serious attention. Half a watt can sound absurdly small until it is placed inside a spacecraft where the total available electrical power has been declining for decades. A half-watt motor left running on the LECP sensor is therefore not wasteful by default. It is an option preserved at a measurable cost. If a later reconfiguration creates enough margin, that little preserved pathway may matter. This is how late mission engineering differs from ordinary design. In a new spacecraft, engineers choose margins before launch. On Voyager, engineers inherit margins that have already been spent by time. The question is no longer what the ideal spacecraft would carry. The question is what the existing spacecraft can safely stop carrying without losing its ability to answer. Undervoltage protection makes the ledger more serious. If demand rises too close to supply, or supply falls unexpectedly, the spacecraft may protect itself by removing loads. That is rational onboard behavior. But from Earth, an automatic response can look like a sudden loss of a system the team needs. The safest shutdown is often the one chosen deliberately before the spacecraft has to choose for itself. There is a thermal bargain inside every electrical bargain. A heater that is turned off saves power, but the hardware it once protected must now tolerate more cold. A fuel line that gets too cold can threaten pointing. Electronics that drift thermally can threaten command or telemetry. So saving electricity in one place can create risk in another. The ledger has columns that talk to each other. That is why 1 more year is not just a number on a calendar. It is another year in which the transmitter can answer, another year in which remaining instruments may gather unique measurements, another year in which engineers can try a safer configuration. At Voyager's age, time is bought in small units: a load removed, a heater spared or sacrificed, a command sequence redesigned, a protection threshold avoided. There is also a timing issue hidden in the power story. The annual loss is gradual, but the operational effects are not always gradual. A spacecraft can absorb decline for a while because engineers remove loads, change settings, and preserve margin. Then, one event makes the margin visible. A maneuver draws attention to a voltage level. A heater activation triggers a protective response. A transmitter state changes. The decline is slow, but the decisions arrive as moments. That is why 4 watts should not make the story feel small. The number is small only if we imagine Voyager has a comfortable surplus. It does not. A few watts can decide whether a sensor remains on, whether a heater can be spared, whether a voltage threshold is crossed, or whether engineers need to choose between science and stability. Let's make the ledger more concrete. The transmitter is not optional if the mission is to talk. The command receiver and computers are not optional if Earth is to direct the spacecraft. Attitude control is not optional if the high-gain antenna has to keep pointing home. Thermal management is not optional where cold hardware can become unusable. Science instruments are precious, but they sit inside this harsher hierarchy. When power becomes tight enough, science competes against the ability to remain a controllable spacecraft. That competition is the late Voyager mission in one sentence. It is tempting to imagine the end as engineers choosing the last instrument. But the deeper question is whether any remaining configuration can keep the whole communication chain stable. An instrument may be scientifically valuable and still be too expensive in watts. A heater may sound mundane and still protect a component needed for response. A transmitter mode may be essential and still risky if the power system cannot support it cleanly. The phrase power budget is useful because budgets force priorities. You do not pay for everything you love. You pay for what keeps the system alive. Voyager's budget is now so constrained that priorities have become visible to the public as instrument shutdowns. But those shutdowns are only the surface expression of a deeper accounting process that has been going on for years. Every year the same question returns with less room around it. What can we turn off so the answer can still come back? Let's separate science life from communication life. This is the hardest correction emotionally, because it means engineers can keep Voyager alive by making Voyager smaller. Not physically smaller, operationally smaller. A working instrument is turned off. A heater is removed from the budget. A capability that once defined the mission becomes a memory, because the remaining spacecraft needs the power more. That does not mean the mission is over. It means the mission has entered the stage where survival and science compete in the same ledger. At the current NASA instrument status checked for this script lock, Voyager 1 has 2 operating science instruments, the magnetometer and the plasma wave subsystem. Voyager 2 has 3, the cosmic ray subsystem, the magnetometer, and the plasma wave subsystem. The older broad wording on one NASA page can make the count look simpler than it is, but the dated instrument table is the safer source. The table was updated April 17, 2026. Now translate the names. The magnetometer, or MAG, measures magnetic fields. That sounds abstract, but for Voyager, it is one of the ways the spacecraft feels the structure of interstellar space. The plasma wave subsystem, or PWS, listens for waves in the thin charged environment around the spacecraft. It can help scientists infer plasma conditions even when other plasma instruments are off. The cosmic ray subsystem, or CRS, detects high-energy particles. Voyager 2 still has it operating. Voyager 1's CRS was turned off in February 2025 to save power. The Low-Energy Charged Particles Experiment, LECP, is now off on both spacecraft. Voyager 2's was shut down in March 2025. Voyager 1's was shut down in April 2026. The Plasma Science Instrument, PLS, has also left active service. Voyager 1's was off years ago because of degraded performance, and Voyager 2's was turned off in September 2024 to save power. That sounds like a list, but the point is not the list. The point is that science ends in pieces. A spacecraft can lose a particle detector and still measure magnetic fields. It can lose a plasma instrument and still infer some plasma information through waves. It can stop returning one category of science while continuing to report voltages, temperatures, computer states, and command acknowledgements. If we compress all of that into the word alive, we lose the actual answer. Let's use the camera as a boundary marker. Voyager's cameras are not taking pictures now. They were turned off after the planetary encounters. That does not make the current mission fake or dead. It means the mission changed form. The same logic now applies to interstellar instruments. One by one, the operating spacecraft is being reduced to what can still justify its watts. There is a discipline to the order. NASA has said science and engineering teams agreed years ago on shutdown sequences. That is important. These choices are not random reactions to bad news. They are planned sacrifices made under shrinking power. The 2026 Voyager 1 LECP shutdown shows how planned order and current risk meet each other. The instrument was next in the sequence, but the immediate push came from a power margin concern after the February roll maneuver. If undervoltage protection had acted on its own, the spacecraft might have shut down components in a less controlled way. So engineers used the plan before the spacecraft forced the issue. That is a different story from panic. It is controlled narrowing. Now bring the title question back in. How long can Voyager keep talking to Earth? The answer may outlive some of the science. NASA's own framing allows for engineering data after science data becomes limited or ends. That means Voyager could still be telling Earth about itself after it stops telling Earth as much about interstellar space. For a viewer, that can feel like a loss. It is a loss. But it is also how the last science is protected. If shutting down one instrument keeps enough margin for another instrument, or keeps the transmitter and computers alive, then the sacrifice buys time for the remaining conversation. This is why we have to avoid a false all-or-nothing ending. Suppose a future instrument is powered off. That is not the same as silence. Suppose only one science instrument remains. That is not the same as full health. Suppose science ends but engineering telemetry continues. That is not the same as mission value being unchanged. Each state has its own meaning. The survival stack is narrowing, not disappearing in one cut. There is also a human bias here. We remember Voyager for the spectacular things, the planets, the images, the famous distance, but the late mission is built from quieter decisions. Half a watt here, a heater there, a sensor motor left on because it uses little power and might preserve the possibility of reactivation. A command sequence shaped so the spacecraft changes state without crossing a protection boundary. That last detail matters. In the 2026 shutdown, NASA noted that a small part of the LECP, a motor that spins the sensor, would remain on because it uses about half a watt and could help if the instrument is ever restarted after a future power reconfiguration. That is the kind of thinking that defines this stage, not simply on or off. Preserve the option if the cost is small enough. So the spacecraft becomes a set of bets. Which instrument gives the most unique science for the least risk? Which load can be removed without making recovery harder? Which subsystem is essential not because it discovers something, but because it keeps the mission able to answer? That is the bridge from science to communication. A quieter Voyager still has to send something. If fewer instruments are speaking inside the spacecraft, the remaining data still has to be packaged, transmitted, aimed, received, and understood. So now the problem moves from what stays powered to what can cross the dark between Voyager and Earth. The instrument names also reveal what kind of science remains. The magnetometer is a low-power way to keep reading the magnetic environment. The plasma wave subsystem can listen for oscillations that reveal plasma conditions indirectly. Cosmic ray measurements follow energetic particles that pass through the detector and leave signs behind. These are not glamorous cameras. They are quiet sensors for a region no other operating spacecraft has reached. That quietness helps the mission survive. Instruments that do not demand much power are more likely to remain defensible in the ledger. A camera system from the planetary encounters would not fit the current mission even if people wanted new pictures, because pictures are not the late-stage scientific priority and the systems were shut down long ago. The surviving instruments earn their place by returning unique interstellar measurements with relatively manageable cost. The shutdown sequence is also a science decision, not only an engineering decision. Teams have to decide which measurements are most valuable, which instruments overlap in what they tell us, and which capabilities can be lost with the least damage to the mission's remaining purpose. That is not a clean emotional choice. It is a ranking made under constraint. A viewer might ask why any science instrument remains if communication itself is at risk. The answer is that science is still the reason to preserve the communication. If the spacecraft can return even one kind of unique measurement from interstellar space, the whole operating chain has scientific value. But when an instrument threatens the chain by consuming power that the chain needs, the instrument loses the argument. So the late mission is neither pure survival nor pure science. It is science filtered through survival. The spacecraft keeps measuring only where measurement does not break the conditions needed to report the measurement. That is the austere logic of Voyager's final operating years. Before we move on, notice how careful the language has to be around active instruments. A public summary may say 3 experiments remain active on each spacecraft, while a detailed, dated table shows the current instrument-by-instrument state after a recent shutdown. In a living mission, the table matters, the date matters, the specific spacecraft matters. Voyager 1 and Voyager 2 are twins, but they are no longer operationally identical. That is why this script uses the April 17th, 2026 NASA instrument status as the lock point. At that point, Voyager 1 has MAG and PWS on. Voyager 2 has CRS, MAG and PWS on. LECP is off on both. PLS is off on both. Cameras are historical, not current. That prevents the story from pretending Voyager is doing everything it once did. It also prevents the opposite error. Turning instruments off does not mean the mission has already ended. A spacecraft with fewer instruments can still be uniquely valuable because of where it is. Voyager is not one of many probes near Earth. It is in interstellar space, returning measurements no newer spacecraft has yet replaced from that location. Even a narrow instrument set can matter when the observing platform is unique. So the shutdown story has 2 truths at once. The mission is diminished. The mission is still precious. That double truth is what keeps the tone calm. We do not need to inflate the loss into disaster. We also should not soften it into routine maintenance. When an instrument that operated for nearly 49 years goes quiet, something real has ended. But the reason it ended was to keep another part of the mission alive. The viewer should feel that trade as engineering weight. Each instrument shutdown is a sentence in the larger answer. It tells us the final silence is being delayed by sacrifice. Let's slow the signal down to the speed Voyager actually uses. The phrase radio signal can make the link sound smooth, almost modern. It is not. Voyager does not stream back deep space information like a camera feed. It sends carefully structured bits across a distance where even light needs most of a day to arrive. The main useful downlink is X-band. In plain English, downlink means the path from spacecraft to Earth. X-band is the higher frequency radio channel Voyager normally uses to send science and engineering data back home. It is valuable because it can carry the information the mission needs in a form the deep space network can receive and decode. There is also S-band. For Voyager, S-band is involved in commanding and can serve as a low-rate fallback for engineering health and state. But it is not equivalent to normal X-band science return. That distinction became very real in 2024 when Voyager 1's fault protection turned off the X-band transmitter and switched to the weaker S-band transmitter after a command sequence involving a heater. Earth could still reconnect with the spacecraft, but normal science and engineering return were interrupted until X-band operations were restored. That is the chapter in one event. Hearing something is not the same as receiving the normal mission. Now look at the rates. NASA's spacecraft information gives an S-band uplink command rate of 16 bits per second. 16 bits per second is almost nothing by everyday standards. A single typed character usually takes 8 bits in a simple encoding. So, at that scale, you are not imagining images or streams. You are imagining instructions crawling across deep space in the leanest possible form. The normal X-band telemetry rate listed for Voyager is 160 bits per second, that is 10 times 16, but still tiny compared with anything familiar from the internet. It is not a broadband pipe. It is a narrow thread. High-rate plasma wave playback can reach around 1.4 kilobits per second. But that is a special mode, not a general invitation to think of Voyager as sending rich data freely. S-band health and state data can be around 40 bits per second. 40 bits per second can be enough to preserve a thread of engineering knowledge. It is not enough to pretend the spacecraft is operating normally as a science platform. So bitrate is not a trivia number, it is a survival choice. When a signal is faint, slower can be more survivable. If you speak more slowly through noise, the listener has more chance to distinguish the message. Radio systems are more complex than that simple analogy, but the intuition helps. Lower rates can make a weak link more recoverable. The cost is that less information comes home. That trade matters because Voyager's transmitter cannot simply shout louder forever. Power is limited, hardware is old. The signal spreads across space. By the time it reaches Earth, the deep space network is listening for something incredibly faint and structured. Let's be careful with the word weak. Weak does not mean vague. The spacecraft is not mumbling poetry into the dark. It is transmitting in designed modes through a high-gain antenna with frequencies and rates that engineers understand. The weakness is physical. The power at Earth is tiny. The discipline is technical. Everything about the link is designed so a faint signal can still become meaningful data. But the margin is thin. If X-band fails permanently, the mission does not automatically vanish in that same instant. The 2024 fallback showed that S-band could preserve contact in a limited way. But limited is the key word. A fallback thread may help engineers diagnose, command, and recover. It may not support normal science. It may not carry enough detail fast enough to keep every operational state clear. This is another reason the final silence may not look cinematic. The link could become slower before it becomes absent. The data could become less complete. Engineers might hear enough to know the spacecraft exists, but not enough to use it as before. The conversation could thin into a kind of engineering whisper. There is also an asymmetry between sending and receiving. Earth has enormous antennas and power resources compared with Voyager. Voyager has a small old transmitter and a limited electrical budget. When Earth commands Voyager, the ground system can push a carefully aimed signal outward. When Voyager answers, the spacecraft has to make its tiny voice cross interstellar space back to a rotating planet. The same high-gain antenna handles the exchange. It is a dish 3.7 meters across, large for a spacecraft, small compared with the 70-meter antennas on Earth. All the data transmitted from and received at the spacecraft goes through that antenna. The radio link is therefore not just a transmitter problem, it is also a geometry problem. If the antenna points correctly, a faint signal has a chance. If it points wrong, a healthy transmitter can become almost useless to Earth. That is why the phrase "keep talking" is doing so much work. Talking means the transmitter still functions. It means the data are formatted into a mode worth sending. It means the rate is slow enough and clean enough for reception. It means Earth has the right dish at the right time. And it means the spacecraft is aimed. A wide, modern communications mindset does not help us here. Voyager teaches the opposite. A conversation can be 160 bits per second and still be one of the most valuable conversations humans have ever maintained. It can be 40 bits per second and still matter if those bits reveal the spacecraft's state. It can be a carrier first, then a diagnosis, then a recovery, then science again. So the weak signal is not just what remains after distance has done its damage. It is the form the mission takes when every bit must justify the what's behind it. But a signal that exists still has to be collected, and part of Voyager's survival is not on Voyager at all. The data rates also change how we imagine information. At 160 bits per second, patience is not a mood, it is built into the link. A short engineering frame can matter more than a rich stream. A carefully selected data product can be more valuable than a flood the spacecraft cannot afford to send. Voyager's communication is not abundant enough for waste. Frequency names can sound arbitrary, so keep them tied to function. X-band is the workhorse downlink for normal science and engineering return. S-band is part of the older, lower-rate command and fallback picture. When Voyager 1 dropped to S-band in 2024, the team had a way to preserve contact, but not a replacement for the normal X-band mission. That difference is the story. The transmitter question is also a power question. A radio does not speak for free, it consumes part of the electrical budget, and the usefulness of that consumption depends on whether Earth can decode the result. If a mode costs power but returns too little meaning, it becomes harder to justify. If a lower rate mode preserves a path for recovery, it may be worth everything for a short time. There is also a clock hidden in every bit. The longer a data return takes, the more DSN time it consumes and the slower a diagnosis becomes. Low rates can make faint links possible, but they stretch operations. That trade may be acceptable for a distant spacecraft, but it means recovery cannot be rushed simply because people on Earth want a quick answer. So the radio link is a discipline of scarcity. Scarce power, scarce bits, scarce ground time, scarce margin. The achievement is not that Voyager sends a loud message. The achievement is that, under those constraints, it can still send enough structure for Earth to turn a whisper into knowledge. There is another reason the weak signal chapter matters. It teaches us not to confuse emotional contact with operational contact. A faint recovered tone can feel like a miracle, and sometimes it is genuinely moving. But mission operators need more than reassurance. They need data that can guide decisions. If the spacecraft can only tell Earth that it exists, Earth may still not know what to do next. If the spacecraft can send health data but no science, the mission has entered a different state. If it can send science only slowly and intermittently, the science plan has to fit the link. The radio does not merely carry the mission, it shapes the mission. Let's also be careful with the word weak. Weak does not mean poorly designed. Voyager's signal is weak at Earth because physics makes it weak. Radio energy spreads, distance dilutes. The transmitter is limited by onboard power. The antenna has a fixed size. The receiving system has noise. A strong design can still produce an extraordinarily faint received signal after interstellar travel. That is why lower data rates are not embarrassing. They are survival tools. Slowing down lets the receiver spend more time on each bit. It improves the chance that the intended signal can be separated from noise. In everyday life, slow communication feels like failure. In deep space operations, slow communication can be what keeps meaning alive. This changes the way we think about a final message. A real final contact would probably not feel like a dramatic paragraph from the spacecraft. It might be a health frame, a partial data return, a carrier reacquisition, a command response, or a failed attempt to restore a mode. The public imagination wants words. The mission speaks in states. So the end may be the moment those states can no longer support action. Not the moment no radio energy leaves Voyager. The moment Earth no longer receives enough ordered information to continue the mission as a mission. Now the weak signal needs a listener, and the listener is not one dish. It is a network built across Earth. Let's move the story back to Earth. Picture a radio dish under the night sky. It is not listening to silence in a poetic sense. It is part of a working machine, one end of a link that stretches from Earth to a spacecraft beyond the planets. For Voyager, the Earth side of the conversation is the Deep Space Network. The Deep Space Network, or DSN, is NASA's global system of large antennas for communicating with spacecraft far from Earth. It receives science and engineering data. It sends commands. It provides the ground half of missions that cannot use ordinary near-Earth communications. The three main complexes are spaced around the world: Goldstone in California, Madrid in Spain, and Canberra in Australia. The spacing matters because Earth turns. A spacecraft may set from the view of one complex and rise for another. For many missions, the network acts like a relay of visibility across a rotating planet. Voyager adds a harder constraint. Not every antenna is equally useful for every part of the conversation. The famous scale is the 70-meter dish, about 230 feet across. That is not big for drama. It is big because the signal is faint and the command path is demanding. A dish that large can concentrate sensitivity in a way smaller antennas cannot. It turns an almost impossibly weak arrival into something engineers can work with. Now separate two jobs. Receiving is Earth listening for Voyager's downlink. Commanding is Earth sending instructions powerful and precise enough for Voyager to receive them. A system can be excellent at hearing and still face constraints when it has to command. For the Voyagers, NASA JPL has described Canberra's DSS-43, the 70-meter antenna in Australia, as the only dish with enough signal power to send commands to the spacecraft. That sentence should be handled carefully. It is not a license to make broad present tense claims about every hour of availability. It is a mission-specific dependency from NASA's reporting, especially important during the 2025 DSS-43 upgrade period. The safe point is this: Earth-side hardware is not background scenery. It is part of Voyager's survival stack. The 2025 roll thruster story makes that concrete. Before DSS-43 went offline for upgrades, the Voyager team wanted to revive backup roll thrusters on Voyager 1. Those thrusters had been considered unusable for decades. The timing was not random. If the spacecraft needed certain commands and the key command antenna was unavailable, an onboard pointing problem could become harder to manage. So engineers were not merely fixing a spacecraft part. They were fixing it inside an Earth and spacecraft schedule. That is a different picture of communication. We often imagine the spacecraft as the heroic distant object and the ground network as a passive listener. But the mission is co-produced. Voyager has to transmit. Earth has to hear. Earth has to command. Voyager has to answer. The path only exists when both ends can meet in the same link budget. A link budget is the plain accounting of a radio path. How much power leaves one end? How much is lost over distance? How much antenna gain helps? How much noise the receiver must overcome? How much margin remains? You do not need the equations to understand the story. A link budget is the radio version of asking whether a whisper can cross a stadium and still be understood by one person with a very good microphone. For Voyager, the stadium is interstellar space. Scheduling also becomes part of survival. DSN time is shared across many missions. A Voyager contact is not just a sentimental check-in with an old probe. It is a planned use of rare ground resources. If engineers need a long track to receive weak data, or a command window tied to a specific antenna, the calendar matters. This is where the phrase "still talking" becomes two-ended. A spacecraft can be technically capable of sending a signal, but if the ground system cannot observe at the required time, or if the needed command asset is unavailable, the operational conversation changes. The spacecraft may not have failed, the link may have. The DSN also affects recovery rhythm. If an anomaly happens, engineers need data. To get data, they need scheduled listening. To respond, they may need a command pass. Then they wait through light time for the command to arrive and for the result to come back. Ground availability and interstellar delay stack on top of each other. That is why the DSN is not a generic NASA aside. For Voyager, it is almost an extension of the spacecraft. The old machine carries the transmitter and antenna. Earth carries the giant ears and the powerful voice. The mission lives in the meeting between them, and the meeting has to be precise. The dish on Earth has to point, the frequency has to be right, the timing has to be known, the data mode has to match, the spacecraft's antenna has to be aimed back. There is romance in the image of a dish listening to the dark, but the actual achievement is disciplined alignment. The deeper we go, the less the question looks like distance. Distance is the stage. The working answer is infrastructure plus power plus pointing plus time. So even if the spacecraft has power, and even if the transmitter can send, Voyager still has to do one deceptively fragile thing. It has to keep its dish pointed home. The DSN also gives Voyager a planetary scale. The spacecraft is small, old, and power limited. The ground system is enormous, distributed, and constantly scheduled. The conversation works because those two unequal machines meet each other. One end concentrates a weak signal through a small dish in deep space. The other end uses giant antennas, sensitive receivers, and planned tracks on a rotating Earth. Commanding is the less intuitive half. Listening to a faint signal is already impressive, but sending a command to a receiver billions of miles away requires its own power, precision, and timing. The command has to arrive at the spacecraft strong enough and clean enough to be recognized. If the needed command asset is constrained, the spacecraft's autonomy and existing state become more important. The camera example matters because it turns infrastructure into narrative. A ground antenna upgrade on Earth can shape what engineers must do aboard Voyager before the outage. That sounds backwards until the whole chain is visible. The spacecraft and the ground are one operating system separated by interstellar distance. Let's picture the antenna as the mission's mouth. That image is not technically complete, but it points us in the right direction. Voyager's useful signal is not a lantern shining equally in every direction. It comes through a high-gain antenna, a 3.7-meter dish aimed back toward Earth. High gain means the antenna concentrates radio energy in a preferred direction. That makes the link stronger where it is aimed and much weaker where it is not. So a working transmitter is not enough. If the high-gain antenna points away from Earth, the spacecraft can lose the conversation even while parts of the radio system still function. The signal does not have to disappear at the source. It can miss the listener. This is why attitude control is communication hardware. Attitude does not mean mood. It means orientation, which way the spacecraft is facing. Voyager has to maintain the right orientation so the antenna stays aimed at the tiny target of Earth and the Sun from that enormous distance. The subsystem that handles orientation is the Attitude and Articulation Control Subsystem, or AACACE. The name sounds like a box in a spacecraft diagram, but the function is simple enough. It keeps Voyager pointed correctly. It controls attitude maneuvers. It supports the orientation that lets commands arrive and data return. The thrusters are part of that story. They are not pushing Voyager onward in the popular sense. The spacecraft's deep space trajectory is not being driven by little rockets every day. The thrusters make small orientation adjustments. They gently tilt the spacecraft so the antenna keeps pointing toward Earth. That makes them communications hardware too. In 2024, Voyager 1 had a thruster problem that shows the risk clearly. Some thruster tubes had become clogged over time, reducing the efficiency of the system used to keep the spacecraft pointed. Engineers worked through a branch switch, warming and using thrusters in a way that preserved pointing capability. The purpose was not dramatic navigation, it was keeping the signal path alive. A later 2025 case adds another layer. JPL revived backup roll thrusters on Voyager 1 before a command pause tied to DSS-43 upgrades. Roll control matters because the spacecraft has to stay oriented relative to a guide star and maintain the geometry needed for its antenna. A roll problem can become a communication problem if it prevents the spacecraft from holding the right attitude. Let's avoid turning that into celestial navigation fog. The plain version is this: Voyager has to know how it is oriented. It has to make small corrections. The hardware that makes those corrections has to work after decades in space, and Earth has to be able to command and verify those corrections through a delay of almost a day each way. That chain is fragile in a different way from power. Power is a shrinking budget. Pointing is a geometric requirement. You can have enough electricity and still lose Earth if the antenna is not aimed. The age of the thrusters matters because thrusters are physical devices. They involve propellant, valves, lines, and tiny firings. Over decades, residue can accumulate. Heating choices become harder because heaters cost power. A line can be too cold. A branch can be less available than it once was. Every fix has to respect the power ledger we just traced, so the stack folds back on itself. You need power to keep attitude hardware usable. You need attitude to keep the radio link usable. You need the radio link to get the telemetry that tells you whether attitude hardware is behaving. You need the DSN to command changes, and every step is delayed by light time. This is why Voyager does not need one grand failure to stop talking. A pointing margin can thin. A thruster branch can become risky. A command needed to correct orientation can be delayed or constrained by ground availability. The spacecraft might still be alive, warm enough and partly powered, yet unable to hold the geometry that makes it audible. Now scale the target. From Voyager, Earth is not a globe in the sky. It is a direction near the Sun, a tiny radio target across billions of miles. The high-gain antenna does not need human-level pointing perfection, but it does need to stay within the mission's communication geometry. At this distance, small angular errors matter because the useful beam is concentrated. That is the hidden difficulty behind the simple phrase aimed at Earth. It sounds like pointing a dish at a planet. Operationally, it is decades of control loops, star references, thruster firings, command sequences, and ground verification. If Voyager's signal were broadcast equally in all directions, the power problem would be worse, because the energy would spread everywhere. The high-gain antenna makes the weak transmitter useful by focusing it. But focus creates dependence. The better the antenna helps when it is aimed, the more the mission needs that aim to survive. So pointing is not a side chapter. It is the place where communication becomes physical orientation. The spacecraft has to face home to speak home. At this point, the conversation has narrowed again. Power decides what can stay on. The radio decides what can be sent. Earth's antennas decide what can be heard and commanded. Pointing decides whether the signal reaches the right place at all. What remains is the slowest part of the chain, how Earth diagnoses and repairs a problem when every answer arrives from yesterday. Pointing also explains why small mechanical details become existential. A clogged thruster tube does not sound like the end of a mission. But if the tube is part of the system that keeps the antenna aligned, the clog is tied directly to communication. The question is not whether the spacecraft can move through space. It is whether it can hold the attitude needed to speak toward Earth. The guide star language in the roll thruster story is easy to overcomplicate. The simple idea is that Voyager uses references to know how it is oriented. Roll control helps maintain that orientation. If the spacecraft cannot control roll reliably, the high-gain antenna and the rest of the spacecraft geometry may drift away from the required communication state. A star reference becomes part of a radio link. There is a power cost here too. Warming thrusters, operating heaters, and choosing a branch are not free moves. The team may need heat to make a propulsion component usable, but heat draws power from the same shrinking budget that supports instruments and communication. A pointing fix can therefore force a power choice. This is why the antenna points at Earth is not a static description. It is an ongoing achievement. The spacecraft has to maintain that pointing through time, hardware aging, thermal changes, and command delay. Every successful contact quietly confirms that many small orientation decisions have remained good enough. If the final failure is pointing, the ending may feel especially strange. The spacecraft could still have a working computer, some power, and even a transmitter, but the focused beam would no longer meet Earth. Silence, in that case, would not mean the voice ended. It would mean the voice turned away. There is a quiet cruelty in the pointing problem. It is both mechanical and informational. If the antenna is pointed well enough, Earth can receive the telemetry needed to judge pointing. If it points too poorly, the data needed to diagnose the problem may disappear with the signal itself. The symptom can remove the instrument used to understand the symptom. That is why attitude control sits so close to the mission's edge. A power issue may give warning through voltage trends. An instrument shutdown can be planned. A data format problem may leave a carrier. But a severe pointing loss can make a living spacecraft look silent simply because its voice is aimed away from the listener. The high-gain antenna also explains why tiny changes matter. At interstellar distance, Earth is an extremely small target direction. The spacecraft does not point like a human aiming a flashlight across a room. It maintains an engineered geometry across billions of miles. The pointing tolerance, antenna beam, and receiver sensitivity together decide whether a weak transmission becomes a usable signal. This is why thrusters that sound like propulsion hardware are really communication hardware now. Voyager is not using them to chase a destination. It is using them to preserve orientation. A clogged thruster line, a warmed branch, a revived roll thruster. These are not side stories. They are chapters in the survival of the radio link. Pointing is also where the age of the spacecraft becomes physically intimate. The old machine has to keep doing small, precise things, not heroic things, small things. Tilt slightly, hold attitude, roll correctly, keep the dish aimed, repeat. Do that with aging hardware, narrowing power, long delays, and limited confirmation. The final loss of pointing would be sharp because it could leave so much else intact. The RTGs may still produce power. The transmitter may still be capable. The computers may still run. But if the dish cannot deliver the signal toward Earth, the mission can end as a conversation. That is why delay comes next. Pointing errors, like every other fault, cannot be corrected instantly. The correction has to cross the same distance as the signal. Let's send one command and wait with it. A command leaves Earth through the deep space network. It travels at the speed of light, which is the fastest anything can carry information. For Voyager 1, recent NASA JPL language puts the one-way light time at over 23 hours, or about 23 hours depending on the exact date and distance. For Voyager 2, recent mission statements put it around 19.5 hours. That sounds slow. It is slow. But the real operational cost appears when you count the return. If a command takes about 23 hours to reach Voyager 1, the spacecraft cannot even begin responding to that command until nearly a day after Earth sent it. Then the result has to travel back for roughly another 23 hours. A single command and confirmation cycle is therefore close to 2 Earth days before engineers know whether the intended thing happened, and many operations are not one command. They are sequences. A step is sent. The spacecraft executes part of it. Telemetry returns. Engineers study the delayed result. Then another step is prepared. If the data are ambiguous, the next step may have to wait for another pass, another command, another return. A recovery that sounds like a single fix in a news paragraph can consume days or weeks in operational time. The 2026 LECP shutdown gives a simple example. NASA said the commands would take about 23 hours to reach Voyager 1. The shutdown process itself would take about 3 hours and 15 minutes. Then Earth still had to receive confirmation, so the event was not instantaneous from the team's perspective. It was a carefully timed action sent into deep space, performed later by the spacecraft, and understood later still by people on Earth. This is why just reboot it is the wrong mental model. A modern device on a desk gives immediate feedback. A light changes. A screen returns. A log appears. Voyager gives old answers. Engineers never see the spacecraft exactly as it is now. They see what it was when the data began crossing the distance. Let's call it yesterday's spacecraft. That phrase is not exact for every moment, but it is emotionally and operationally right. The spacecraft being diagnosed is already in the past. If a command fixes something, Earth learns that the fix worked after the fact. If a command makes something worse, Earth learns that after the fact too. The delay also changes risk. A command sequence has to be more carefully built because improvisation is expensive. If the first response is unexpected, the team cannot nudge the machine in real time. They have to stop, interpret, model, and send the next instruction through the same delay. This is where Voyager's age and distance reinforce each other. Old hardware creates unusual faults. Distance makes every unusual fault slow to understand. During Voyager 1's 2023 to 2024 flight data system problem, engineers had to work through limited information to restore usable data. They recovered engineering updates first, then science data later. That order matters. Engineering telemetry tells you about the spacecraft. Science data tells you about the environment. In a recovery, the health report often comes before the full scientific return. That sequence is not a narrative flourish. It is how operations become possible. You need to know enough about the machine to trust the next command. You need enough decoded telemetry to decide whether the workaround is safe. You need to separate a data formatting problem from a hardware death. Now add the Deep Space Network's schedule. The command cannot leave through any imaginary always-on pipe. It has to use the right ground assets at planned times. The return has to be received and decoded. If the spacecraft is in a limited mode, the data rate may be low. If the signal is weak, the pass may need careful handling. The round-trip delay is only the minimum clock. The operational clock can be longer. This is why patience is not just a virtue in Voyager operations. It is a physical requirement. The delay also explains why fault protection is both necessary and dangerous. The spacecraft cannot wait a day for Earth to approve every immediate safety response. It needs onboard routines that can protect it when something crosses a boundary. But if those routines turn off a transmitter, change a mode, or shed a load in a way Earth did not expect, the team inherits a puzzle with a 2-day echo. So command delay is not separate from the systems we have already traced. It changes how power decisions are made. It changes how transmitter fallbacks are recovered. It changes how pointing problems are handled. It changes the meaning of every anomaly. There is a quiet beauty in this, but it is not the beauty of distance alone. It is the discipline of acting without immediacy. Engineers write instructions for a machine that will receive them tomorrow. They listen to a reply from the machine as it was yesterday. They maintain confidence by building each action so it can survive the delay. That is why the conversation is still a conversation. Slow, narrow, delayed, and old, but not passive. Earth asks, Voyager answers, Earth waits, Voyager acts. The rhythm is almost geological compared with modern control, but it remains operational. Delay would be hard enough with a simple machine. Voyager is not simple. Its old computers can fail in ways that are difficult even to describe from Earth. The delay also changes accountability. Engineers cannot test a guess cheaply. On Earth, a bad guess can be corrected seconds later. With Voyager, a bad guess may consume days and create a new state that is already old when confirmed. So every command has to be conservative enough to protect the spacecraft and bold enough to change something useful. This is why command sequences are designed rather than improvised. A sequence is a small script for the spacecraft. Do this, then hold this state, then report. The spacecraft executes from its onboard logic. Earth does not watch each line happen in real time. The design has to anticipate the machine's behavior without immediate supervision. Light time also affects emotion. From Earth, people may be waiting for a confirmation that technically belongs to the past. The spacecraft has already acted, or failed to act, long before the team knows which. That delay creates a strange humility. Human intention reaches Voyager only after the universe has imposed a day of distance on it. For recovery, the practical result is stepwise confidence. First, confirm contact, then confirm a data mode, then confirm health, then send a limited command, then compare the response. Each step narrows uncertainty. Skipping steps may save calendar time, but it can spend safety margin the mission cannot replace. So command delay is a filter on every other solution. A power fix, a transmitter recovery, a thruster warming, a computer workaround, all of them must be possible inside the slow rhythm of interstellar command and reply. If a future problem requires fast human intervention, Voyager may not be able to receive it fast enough for the mission to survive. There is one more consequence of delay before we move inside the computers. Delay makes every operational state provisional. Engineers never know the spacecraft exactly as it is right now. They know it as it was when the signal left. By the time the data arrives, the onboard state has already continued forward. That does not make the mission impossible. It makes planning essential. Commands have to assume the spacecraft state at the time of arrival, not merely the state seen at the time of transmission. If a sequence is running, if a voltage margin is tight, if an automatic routine might intervene, the difference between Earth time and spacecraft event time matters. This is especially important for recoveries. A recovery can involve a diagnostic command, a wait, a data return, a new interpretation, and another command. Each step depends on the last return. Each return is delayed. The chain can stretch for days or weeks, not because anyone is slow, but because physics is. Delay also makes humility operational. If you cannot see now, you do not pretend to control now. You build robust sequences. You avoid unnecessary risk. You accept that confirmation is part of the action, not a formality after it. A command has not truly become an operational success until the reply returns and can be understood. That changes how we hear the phrase mission operations. It is not a room of people simply steering an old probe. It is a disciplined process for acting under permanent latency. Engineers plan, send, wait, compare, and then decide again. The spacecraft has to remain stable during the waiting, because Earth cannot compress light time by wanting an answer faster. That is why old onboard systems matter so much. Between Earth commands and Earth confirmations, Voyager has to keep managing itself. The computers are not glamorous. They are the spacecraft's ability to remain coherent while Earth waits. Let's avoid the word computer for a moment and ask what each system actually does. Voyager is not carrying one modern brain. It has several computer subsystems with different jobs. The Command Computer Subsystem, or CCS, handles command decoding, sequencing, fault routines, and parts of spacecraft control logic. The Flight Data System, or FDS, collects and formats science and engineering data. The Attitude and Articulation Control Subsystem, AACS, controls orientation and helps keep the high-gain antenna pointed toward Earth. Those names are not important because they are acronyms. They are important because each one sits in the communication chain. The CCS helps Voyager understand what Earth is asking. The FDS helps Voyager prepare what it sends back. The AACS helps Voyager keep the antenna aimed so the message has somewhere to go. If any of those functions fails in the wrong way, talking to Earth changes. NASA's FAQ describes the spacecraft computers as processing about 8,000 instructions per second. That number is almost comically small next to modern electronics, but the comparison can become lazy if we treat it as a joke. The point is not that a phone is faster. The point is that Voyager's old computers are doing exactly the kind of limited, mission-specific work they were built to do, and they are doing it with almost no margin for replacement. A modern computer can be patched, swapped, rebooted, or physically accessed. Voyager's computers can only be commanded through the link we have been tracing. Any workaround has to fit the old architecture, the remaining memory, the power budget, the data rate, and the delay. The duality, the 2023 to 2024 FDS anomaly shows why this matters. The spacecraft was still present. but the data coming back were unusable. That is a very specific kind of failure. It does not mean the antenna vanished. It does not mean the transmitter could not produce a signal. It means the system responsible for preparing meaningful information had broken the conversation's grammar. Imagine hearing a voice through a wall, but every word has been scrambled into nonsense. The presence is real, the message is not useful. Engineers eventually restored engineering updates and then science data. The order is revealing. First, recover enough health information to know what the spacecraft is doing. Then recover the scientific measurements. The mission's value depends on both, but operations depends on telemetry first. Telemetry formatting sounds boring until it fails. Then it becomes the difference between a machine that can explain itself and a machine that can only be detected. Fault protection adds another layer. Fault protection means onboard routines that respond when the spacecraft detects an unsafe or unexpected condition. In plain terms, Voyager has some ability to protect itself when Earth is too far away to react immediately. The evaluation is the important part. Fault protection is one reason the spacecraft survives, but it can also interrupt the very link needed to understand what happened. The 2024 transmitter event is a good example. A command involving a heater was followed by fault protection turning off Voyager 1's X-band transmitter and switching to S-band. From the spacecraft's perspective, that response was protective behavior inside an old system with thin margins. From Earth's perspective, it changed the communication mode and temporarily limited normal data return. Protection preserved the spacecraft but complicated the conversation. That is the tension. Autonomous routines are necessary because the spacecraft cannot wait for Earth on every immediate safety issue. But autonomy in an aging machine can create surprises. A protective action that made perfect sense in the logic of the spacecraft may remove a capability engineers were relying on. Now return to power. Computers need electricity. Memory states need stability. Transmitters and heaters compete for watts. If the power margin becomes too thin, the spacecraft can cross thresholds where the computers themselves have to protect the system. So the old computers are not separate from the shrinking RTG budget. They are the place where electrical reality becomes operational behavior. Return to pointing. AACS helps keep the antenna aimed. If orientation information is wrong, or attitude control commands cannot be executed correctly, the communications link is at risk even if the radio is healthy. So the old computers are not separate from the antenna story either. Return to science. FDS has to collect and format instrument data. If an instrument is on but the data path fails, the measurement may never become useful to Earth. So an operating science instrument is only part of science return. The data system has to make the measurement speak. This is why the late Voyager mission is not simply waiting for one hardware part to die. It is managing a web of old functions that must keep agreeing with one another. Commands have to be decoded, data have to be formatted, fault routines have to protect without trapping the mission in an unhelpful state. Orientation has to be maintained. All of it has to be understood through limited telemetry. The most dangerous failures may not be visually dramatic. A corrupted memory location, a timing mismatch, a protection response triggered by a load, a formatting problem that turns good measurements into unreadable return. These are quiet ways for a mission conversation to weaken, and yet this is also where Voyager's endurance becomes more impressive. It is not merely surviving because it is simple. It is surviving because teams still understand enough of its old complexity to work around problems from billions of miles away. These protective systems are why Voyager survives many faults. But at this age, recovery itself has become part of the mission. The old computers also define what kind of instructions are possible. Engineers cannot simply upload a modern software environment or ask the spacecraft to behave like a current probe. Commands have to fit the architecture Voyager has. Workarounds have to respect memory limits, timing, and the way subsystems talk to each other. The repair has to belong to the old machine. That is why the FDS problem was so revealing. If the data path is wrong, the spacecraft can be doing valuable work internally while Earth receives nonsense. The failure is not in the measurement alone and not in the transmitter alone. It is in the translation from onboard state to Earth-readable information. Communication requires grammar. Fault protection has its own grammar. The spacecraft watches for conditions that look unsafe, and it follows built-in routines. Those routines were designed to save the probe when Earth cannot act quickly enough. But the spacecraft is now older, colder, lower on power, and farther away than at any earlier point. A protective routine may still be logical while producing an operational headache. The computer story also changes the meaning of telemetry. Telemetry is not just data about the spacecraft. It is the evidence needed to decide whether the computers are still trustworthy. If a counter changes, if a memory address behaves oddly, if a fault flag appears, the team has to decide whether it represents the true spacecraft or a damaged report about the spacecraft. So the old computers are not a quaint limitation. They are the layer where physical survival becomes interpretable. Without them, instruments cannot explain what they measured, commands cannot become action, and protection cannot be understood. The mission's voice passes through their aging logic before Earth hears it. The computer chapter also clarifies why a simple reboot analogy is dangerous. On Earth, when a device misbehaves, rebooting can feel harmless. In deep space, a reset is not a casual gesture. The spacecraft may come back in a configuration that needs careful commanding. It may require a transmitter mode, a pointing state, a memory path, or a sequence schedule that cannot be assumed. Voyager's computers were built with redundancy, routines, and fault protection. But redundancy ages too. A backup path that exists on a diagram may not be equally attractive after decades of radiation, thermal cycling, power changes, and prior use. Engineers have to know not only what was designed, but what has actually survived. That is why the FDS anomaly was so instructive. The recovery was not just finding the broken part. It was finding a way for an old system to express meaningful information again. In a mission where the data rate is tiny and the delay is huge, restoring meaning is restoring the mission. The onboard computers are also where science becomes communicable. A measurement that cannot be formatted is not science returned to Earth. A command that cannot be sequenced is not control. A pointing correction that cannot be executed is not pointing. The computers convert physical capability into operational capability. So when we talk about old computers, we are not indulging nostalgia for low processing speeds. We are talking about the minimum onboard intelligence required for a spacecraft to remain part of a two-ended operation. The intelligence is modest by modern standards, but the task is severe. Keep order, protect the spacecraft, format the answer, accept the next instruction. Do it all with almost no room for confusion. If that layer thins too far, recovery itself becomes hard to recover. Let's use the anomalies as a map, not a headline. A Voyager anomaly is not automatically a lost spacecraft crisis. The word anomaly only means something is not behaving as expected, but at this distance and at this age, every anomaly consumes margin. It demands DSN time. It demands engineering attention. It demands commands sent into delay. It may require the spacecraft to operate in a reduced mode while the team reconstructs what happened. The first case is the flight data system problem. Voyager 1 returned unusable data even though the spacecraft itself had not vanished. That case maps the boundary between contact and understanding. A carrier can exist, a radio path can exist, but if the data system cannot format meaningful information, Earth does not receive the story it needs. The recovery also shows the order of trust. Engineers restored engineering telemetry before full science return. That is how you rebuild confidence. First, learn the health of the machine. Then bring back the measurements from the environment. It is patient, layered work, not a single heroic button press. The second case is the 2024 transmitter switch. Fault protection turned off the X-band transmitter, and the spacecraft fell back to S-band. This maps the boundary between normal return and limited contact. Earth could reconnect, but the mission was not in its usual data state. S-band preserved a thread, X-band had to be restored for regular operations and science data. That case proves the transmitter is not one simple voice. Voyager has modes, and those modes have different meanings. A fallback can be a lifeline without being a full mission. The third case is thruster and roll control recovery. This maps the boundary between radio hardware and antenna geometry. The spacecraft needs tiny orientation adjustments so the high-gain antenna keeps pointing back toward Earth. Clogged thruster tubes, old branches, and roll control issues are therefore not just attitude control trivia. They are threats to the ability to keep the signal aimed. The fourth case is the 2026 power drop and LECP shutdown. This maps the boundary between science capability and spacecraft preservation. The instrument was valuable, it had worked for almost the whole mission, but the power margin had become thin enough that proactive shutdown was safer than waiting for undervoltage protection to act on its own. Together, these cases show the stack under stress. One problem tests data formatting, one tests transmitter mode, one tests pointing, one tests power triage. None of them needs fake drama to matter. The drama is already in the constraints. Let's look at how recovery actually feels in operational time. Engineers notice a changed signal or unusable data. They gather what telemetry they can. They compare that limited information with old documentation and current spacecraft models. They design a command or sequence. They wait for a DSN opportunity. They send it. The command takes many hours to arrive. The spacecraft acts. The reply takes many hours to return. Then the team decides whether the next step is safe. That is one cycle. A real recovery may need many. This is why the public version of events can sound deceptively simple. Voyager resumes regular operations is true, but it compresses a long chain of uncertainty and verification. The spacecraft did not just come back like a laptop waking from sleep. The team had to rebuild a working state through a link that delivers old answers at tiny rates. There is also no guarantee that the same style of recovery will always remain available. Every successful workaround uses remaining margin. It may rely on a transmitter that still works, a thruster branch that can still be warmed, a computer that still accepts a patch, a DSN antenna that can still command, and enough power to perform the steps. As the mission narrows, each future recovery has fewer comfortable options. That is not pessimism. It is the honest consequence of the stack. Voyager's recent history is therefore not a list of scares. It is a preview of possible endings. A data system problem could one day not be recoverable. A transmitter fallback could one day be too limited. A pointing issue could one day exceed what thrusters can correct. A power protection event could one day remove something essential before Earth can intervene. The team works against those possibilities with planning rather than panic. Shutdown orders are agreed in advance. Commands are tested as far as possible. Ground assets are scheduled. Old hardware options are revisited. A thruster branch considered unusable decades ago can be revived if the alternative is worse. That kind of engineering is easy to understate because it is not cinematic. It is not a rescue scene. It is constraint management at the edge of contact. And it changes how we should hear the phrase still operating. Still operating does not mean trouble-free. It means problems remain diagnosable, commandable, and recoverable enough that the mission continues. That is a high bar now. The anomalies also teach restraint. A fake version of the story would treat every communication pause as if NASA had lost Voyager forever. A shallow version would treat every recovery as proof the spacecraft can always be saved. The useful version sits between those. Each event reveals which layer was threatened and which layer still held. So by now, the answer is no longer hiding in distance alone. Voyager has survived because each threatened part of the conversation has been repaired, reduced, or worked around. The next question is what happens when the threatened part cannot be worked around. Each recovery also has a hidden opportunity cost. While the team is diagnosing one problem, power continues to decline, DSN time is being used, and other risks do not stop existing. A recovery campaign is not outside the aging process. It happens inside it. That makes speed valuable, but speed cannot override caution. The recoveries also show how layered success can be. Reacquiring a signal is one success. Decoding engineering data is another. Restoring science return is another. Returning to regular operations is another. Public headlines may compress all of that into "Voyager is back," but operations lives in the layers between lost and back. There is an important non-miracle quality to the work. Engineers are not defeating physics. They are respecting it with unusual patience. They use the data rate available, the power margin available, the hardware options available, and the ground windows available. The achievement is not magic. It is disciplined constraint solving. That distinction protects the future answer too. We should not assume every future anomaly can be recovered because several recent ones were. The same stack that allowed recovery is thinning. A workaround that was possible with one extra watt, one usable thruster branch, or one functioning transmitter mode may not be possible after the next loss. A recovery at the edge is both encouraging and sobering. It proves the mission is still actively managed. It also reveals how many things must remain true for management to work. The end may arrive not because engineers stop trying, but because the spacecraft no longer leaves them a safe move. There is another lesson in the recovery record. Voyager's recent problems are not random anecdotes beside the main story. They are previews of end conditions. The FDS issue previews a world where the spacecraft may be present but unreadable. The transmitter switch previews a world where a fallback mode exists but normal return does not. The thruster work previews a world where pointing becomes the limiting factor. The LECP shutdown previews a world where power conservation keeps winning. Let's build the endings from the chain we have already traced. There may be no cinematic last message, no final sentence, no dramatic farewell packet. Voyager's end as a mission may arrive as a change in state that only becomes clear after engineers fail to recover the next layer of the conversation. The first ending is the planned science drawdown. This is already happening. Instruments are turned off one by one to conserve power. In this path, science becomes thinner before contact ends. Voyager may keep sending engineering telemetry after it stops returning meaningful science from active instruments. That would be a real loss, but not immediate silence. The second ending is a minimal science tail into the 2030s. NASA JPL has stated, conditionally, that at least one science instrument could operate into the 2030s if the spacecraft remain healthy. The words "if healthy" do real work. They include power, hardware, thermal state, transmitter function, pointing, and recoverability. The 2030s are not a promise. They are a possible window if the stack holds. The third ending is engineering-only contact. In that state, Voyager might no longer be doing useful science, but it could still report health information, temperatures, voltages, switch states, computer status. That might sound like a ghost of the mission, but engineering telemetry has value. It tells Earth that the machine still exists as an operating spacecraft. The fourth ending is a carrier-only or near-carrier tail. Earth might detect a signal but receive little meaning from it. This is the thin edge of contact. It tells us the radio path has not fully vanished, but it may not support useful operations. It is the difference between hearing that someone is on the line and having a conversation. The fifth ending is a transmitter or power fault. A future undervoltage event could force the spacecraft to protect itself by turning off components. A transmitter could fail. A powered load could become impossible to carry. The 2024 X-band to S-band event shows the shape of this risk without pretending it has already become final. A fallback can be recoverable once. It may not always be recoverable. The sixth ending is pointing failure. The radio may work, the spacecraft may have some power, but if attitude control can no longer keep the high-gain antenna aimed at Earth, the link can collapse. This is one of the cleanest ways to understand operational silence. The voice may remain, but it no longer points at the listener. The seventh ending is commandability loss before passive detection disappears. Earth might still detect a signal, but be unable to command reliably or confirm response. That would be a profound operational boundary. A mission is not only something we hear, it is something we can work with. If Earth cannot change the spacecraft's state, recover faults, or verify commands, the conversation has become one-sided. The eighth ending is Earth-side link margin. NASA's FAQ language supports the idea that the spacecraft could remain within DSN range through about 2036, depending on remaining power to transmit a signal. About 2036 should not be treated as the date. It is a boundary condition from one source framing. If enough transmit power remains, and the link budget still closes, the DSN may still hear. If not, the date moves. These endings are not equal in probability, and they are not mutually exclusive. They can blend. Science can draw down while transmitter risk rises. Engineering-only telemetry can continue while commandability becomes harder. A pointing issue can combine with low power. A DSN constraint can make a spacecraft side fault harder to recover. That is why the end is better understood as loss of overlap. Let's separate four final states. Science end means the instruments no longer return useful measurements. Engineering tail means the spacecraft still reports its own condition. Carrier trace means Earth can detect something but may not receive enough meaning. Operational silence means Earth no longer gets a useful answer from a controllable spacecraft. Those are different endings. The object continues through all of them. Voyager does not stop moving when science ends. It does not stop moving when telemetry ends. It does not stop moving when Earth no longer commands it. It keeps following its trajectory through space. But the mission as a two-way human operation has changed. This is where popular language fails. We say Voyager dies, but the thing that dies is not the metal object. It is the maintained relationship. A mission is matter plus meaning plus control. Remove the meaning and control, and the matter keeps going. There is also a timing trap. If the final failure is sudden, Earth may only know after the fact. If the final decline is gradual, there may be arguments about when the mission truly crossed the line. Was it when the last science instrument stopped? When engineering data stopped? When commands stopped being confirmed? When the carrier vanished? Different people could choose different markers. The cleanest marker for this video is operational silence. That is the point where Earth no longer receives a useful answer from the spacecraft as a mission. The useful answer may be science. It may be health telemetry. It may be command confirmation. But it has to be useful. A meaningless trace is not the same thing as conversation. So the ending probably will not be one Hollywood moment. It will be a narrowing of modes, a loss of options, and finally a failure of recovery. The team will try to understand. They will use the DSN. They will test what can still be commanded. They will look for a mode, a margin, a workaround. If none remains, the silence becomes the answer. Once the endings are separated, the date question can be answered honestly, not as a prophecy, but as a boundary. One reason the endings blur is that usefulness has thresholds. A data rate may be technically present, but too slow for meaningful science. A command may be sent, but not confirmed with enough confidence. A signal may be detected, but not stable enough for operations. The mission does not cross every threshold at once. The science first ending is the easiest to accept because it already matches the pattern. Instruments have been shut down to preserve power. If that continues, the scientific mission may narrow to one last measurement type, and then no active science at all. That would be historically significant, but it would not automatically make the spacecraft unreachable. The commandability ending may be harder to see from outside. If Earth can still hear a weak signal, Headlines may say Voyager is alive, but if engineers cannot reliably command it, confirm changes or recover faults, the operational mission is fundamentally altered. Control is part of conversation. Without control, contact becomes observation. The pointing ending is cleaner in physics and messier in feeling. A spacecraft with some power and a working transmitter could still be lost to Earth if the beam no longer reaches us. That ending would not look like the machine choosing silence. It would look like geometry becoming impossible to maintain. The ground link ending reminds us that silence is not solely aboard Voyager. The DSN's sensitivity, command power, scheduling and upgrades all live on Earth. If remaining transmit power falls below what the Earth system can close, the conversation ends at the interface between a weakening spacecraft and the best listening system humans can provide. The end scenario map also protects the viewer from a false emotional contract. If a video promises the last signal, the audience waits for one dramatic event. But Voyager may not give us that shape. The final years may be administratively clear and emotionally ambiguous. A shutdown may be planned, a recovery may fail, a faint return may continue after science is over, a carrier may be detected after commandability is no longer meaningful. That ambiguity does not make the ending weaker, it makes it more real. Spacecraft do not end their missions for narrative convenience. They cross operational thresholds. The thresholds may be obvious only after engineers compare several passes, several failed attempts, several narrowing options, and a final conclusion that further contact is no longer useful or possible. So the job of this script is not to manufacture a final scene, it is to make the actual boundary visible enough that a quiet ending still feels complete. If the final loss is power, we understand why watts mattered. If it is pointing, we understand why the dish mattered. If it is commandability, we understand why uplink and DSS-43 mattered. If it is telemetry meaning, we understand why FDS mattered. If it is link margin, we understand why DSN and data rate mattered. That is the payoff of the stack. The ending can take several forms, and the viewer is prepared for all of them without being misled by any one of them. This is also where we avoid turning uncertainty into vagueness. We can be uncertain about the exact day and still be precise about the mechanisms. We can refuse a fake countdown and still answer the title. The honest answer names the decade, the source limits, and the conditions that decide the final boundary. Now we can answer the date hunger in the only way that respects the evidence. Let's answer the date question honestly. The strongest answer is not a single year. The strongest answer is a staged range with conditions attached. NASA JPL power management statements support the possibility that at least one science instrument could keep operating into the 2030s if the spacecraft remain healthy. NASA's FAQ also says engineering data could continue for several more years after science data stops, and that the spacecraft could remain in range of the Deep Space Network through about 2036, depending on remaining power to transmit back to Earth. That is the supported shape of the answer. Science could continue into the 2030s if enough power and hardware health remain. Engineering contact could outlast science. DSN contact could potentially extend toward about 2036 if transmit power and link margin remain sufficient. None of those statements is a guaranteed final contact date. The word about matters. The word could matters. The phrase, if healthy, matters. Why can't NASA simply calculate the final day? Because the final day is not controlled by one variable. Distance matters, but so does transmitter state. RTG output matters, but so does which loads remain. Instrument health matters, but so do computers and telemetry formatting. The high-gain antenna matters, thrusters matter, fault protection matters. DSN command availability and receiving sensitivity matter. A single fault can move the answer earlier. A successful power reconfiguration can move useful operation later. This is the honest date. Likely staged decline through the late 2020s and into the 2030s, with science narrowing first, engineering and contact potentially lasting longer, and about 2036 as a source-supported DSN range boundary rather than a countdown clock. That sentence is less dramatic than Voyager dies in 2036. It is also much truer. Let's bring the current mutable facts into the answer carefully. At this script log, NASA's Voyager mission page still points to the April 17, 2026 update as the latest major Voyager operational news. The Where Are They Now page still lists the mission status distance table as temporarily offline, while numbers are tuned as Voyager 1 approaches 1 light day later in 2026. The dated instrument table shows Voyager 1 with MAG and PWS on, and Voyager 2 with CRS, MAG and PWS on. Those facts can change. That is not a weakness in the script. It is the nature of an active mission. The Big Bang power saving plan is a good example. NASA described it as an ambitious energy-saving reconfiguration to be tested first on Voyager 2 in May and June 2026, with Voyager 1 no sooner than July if testing succeeds. If it works, it could extend operations and even create the chance of reactivating Voyager 1's LECP. If it fails or is not implemented as hoped, the future power picture changes. So the right way to use that plan is not to promise a rescue. It is to show that the date remains operational, not fixed. Engineers are still trying to reshape the spacecraft's energy budget. The final answer depends partly on whether those reshaping efforts succeed. Now consider the viewer's original hunger. They clicked to know how long Voyager can keep talking. A weak answer would hide behind caveats. A false answer would pretend precision. The useful answer gives the time window and the mechanism. Into the 2030s for at least some science is plausible if health and power hold. Engineering data can outlast science. Around 2036 appears in NASA FAQ, framing as a possible DSN range and contact boundary depending on transmit power. But the actual end of the conversation will be set by whichever essential layer stops overlapping first. That may be power. It may be pointing, it may be transmitter function, it may be data formatting, it may be commandability, it may be the ground link, it may be a combination no one can forecast cleanly. This is not evasive, it is the difference between astronomy as distance and spacecraft operations as survival. If the question were only how far Voyager can travel, the answer would be easy in a different way. It will keep moving. If the question is how long Earth can maintain a meaningful exchange with a 1977 spacecraft, then the answer belongs to a shrinking set of margins. Let's make the date feel physical. Every year, roughly 4 more watts disappear from the electrical budget. Every year, old hardware is asked to keep working longer than it was ever emotionally reasonable to expect. Every year, DSN contact depends on the spacecraft still being able to aim, transmit, format, receive, and answer. The 2030s are not far away in mission terms. They are only a handful of 4-watt declines away. That is why a date range can be more truthful than a date. A range admits that future faults matter. It admits that engineering decisions matter. It admits that a spacecraft can lose science before contact, and contact before physical survival. The satisfying part is not exactness. The satisfying part is visibility. We can now see what will end the conversation. Not age in the abstract. Not distance alone. Not one mythic last signal. The conversation ends when the overlap closes, and that brings us to the final shape of the answer. The date also depends on what we decide to count as talking. If talking means active science data, the window is shorter. If it means engineering telemetry, the window can be longer. If it means any detectable carrier, longer still, but less useful. If it means two-way operational control, the answer depends heavily on commandability, not just detection. This is why about 2036 should be heard as a link margin horizon, not a prophecy. It comes with the condition that enough power remains to transmit a signal the DSN can receive. Change the power. Change the transmitter state. Change pointing. Change a fault outcome. The horizon shifts. The phrase into the 2030s carries a different meaning. It refers to possible science operation with at least one instrument if the spacecraft remain healthy. That is a science life statement, not a guarantee of full communication health. A single surviving instrument would be remarkable, but it would still sit inside all the other requirements. The Big Bang power plan shows why active engineering can alter the range. A successful reconfiguration can buy margin. An unsuccessful one, or a new fault discovered during the attempt, can spend margin. Voyager's future is not a passive extrapolation of 4 watts per year. It is 4 watts per year plus every operational choice made around that loss. So the honest date is a layered answer. Science may narrow through the 2030s if health allows. Engineering may continue beyond the end of science, and DSN contact could approach the mid-2030s if transmit power remains adequate. The final operational silence arrives when the chain can no longer produce a useful reply. The honest date chapter also tells us what to watch from here. Not as breaking news anxiety, but as indicators of the stack. Watch for instrument status changes, because they tell us how science is being traded for power. Watch for power management updates, because they tell us how much margin remains. Watch for transmitter mode language, because X-band and S-band do not imply the same mission state. Watch for AACs and thruster updates, because pointing is communication. Watch for DSN and DSS-43 context, because Earth-side command capability matters. Watch for telemetry recovery language, because usable data is different from a detected signal. Those are the meaningful signals. A dramatic headline saying Voyager is lost may be less useful than a quiet NASA paragraph saying which instrument was powered down and why. A small note about a command sequence may tell us more about the mission's future than a large graphic showing distance. Distance still matters, but it is not the villain by itself. Voyager has already proven that distance can be crossed by patient engineering. The harder truth is that distance makes every other weakness more expensive. A weak transmitter matters more across distance. A pointing error matters more across distance. A delayed recovery matters more across distance. A low data rate matters more across distance. So the date answer is not evasion, it is a demand for the right unit of measurement. The unit is not miles, it is overlap. The unit is not 1 calendar day, it is the survival of enough linked functions to keep a conversation alive. And that is why the final convergence does not need a new fact. It needs the old facts seen together. Let's put the stack back together. Return to the opening image. An old spacecraft is aimed toward a distant Earth. A deep space network dish waits for a signal so faint that the achievement is not just hearing it, but understanding it. At the beginning, that image felt like wonder. Now it is a diagram. The 3.7 meter high gain antenna is not decoration. It is the focused mouth and ear of the spacecraft. The weak transmitter is not a symbol, it is the remaining voice. The old computers are not quaint. They are the systems that decode commands, format telemetry, protect the spacecraft, and keep the antenna pointed. The DSN is not scenery, it is the other half of the mission. Voyager keeps talking only while these things overlap. Power has to be enough, not abundant. Enough. The transmitter has to work in a useful mode, not just any trace, a mode that can carry meaning. The antenna has to point home, not generally outward. Home, the computers have to keep the language intact. Commands in, data out. Faults contained rather than amplified. The instruments, if science is still being returned, have to be powered and healthy enough to measure something worth sending. Earth has to hear, Earth has to command, Earth has to schedule the right assets and close the link, and time delay has to remain manageable enough that recovery is still possible. None of those conditions alone is the mission. Together they make the conversation. This is why the final years of Voyager resist a clean story. The spacecraft can be partly alive in several different ways. It can carry a carrier, it can send engineering telemetry, it can return limited science, it can accept commands, it can also lose one of those before the others. The mission is not a single lamp, it is a set of lights in different rooms, and the end is the moment the remaining lights no longer form a working house. That image matters because it protects us from two mistakes. The first mistake is melodrama, treating every anomaly as the end. The second mistake is complacency, treating every recovery as proof the end is far away. Voyager is neither doomed tomorrow nor guaranteed a graceful final decade. It is operating inside a narrowing overlap. The overlap has held for an extraordinary length of time. Since 1977, the spacecraft has crossed from planetary exploration into interstellar measurement. But for this video, that history is not the main lane. The important fact is that a machine built in that era still participates in a two-way operation with Earth. A command leaves a planet. Nearly a day later, Voyager receives it. The spacecraft acts with old computers, thin power, careful pointing, and a faint radio. Nearly another day later, Earth receives the reply. That is the conversation. Now imagine one layer removed. If science instruments are off, the conversation can continue as engineering. If engineering telemetry is limited, contact may continue as a thinner diagnostic thread. If commandability is lost, passive detection may remain, but the mission is no longer being operated in the same way. If the carrier disappears, Earth no longer even has the radio trace. Each step is quieter than the last. The closing boundary is therefore not when Voyager stops existing. It is when Earth can no longer get a useful answer. The spacecraft does not have to break apart. It does not have to stop moving. It does not have to reach some final wall in space. The mission can end while the object continues. That distinction is the whole answer. How long can Voyager keep talking to Earth? As long as the shrinking power budget, the remaining instruments, the transmitter, the high-gain antenna, the old computers, the fault protection, the thrusters, the command timing, and the deep space network still overlap enough to preserve a useful exchange. The date is conditional because the stack is conditional. And when the overlap finally closes, the silence will not mean Voyager is gone. It will mean the conversation has ended. The overlap is also why Voyager's survival feels different from ordinary longevity. A rock can last for billions of years without doing anything. A spacecraft mission lasts only while matter, power, information, and human operations remain linked. Voyager is extraordinary because that link has survived far longer than the original planetary mission. Every chapter has been one way of removing a false simplicity. Not just distance, not just power, not just signal strength, not just NASA's antennas, not just old computers, not just a date. Each answer was incomplete until it met the others. The final answer is the intersection. That intersection can shrink gracefully for a while. One instrument off, a lower data rate, a longer recovery, a more careful command, a narrower science return. But shrinkage is not infinite. Eventually, the remaining overlap may be too small to contain a mission. When that happens, the most honest language will probably be operational. The team may say they can no longer receive usable telemetry, or can no longer command, or can no longer recover the spacecraft. Those phrases are quieter than Voyager died. They are also more exact. And exactness matters here because it preserves the real wonder. Voyager's achievement is not that it will last forever. It is that, for nearly half a century, a built object has kept answering through a chain of fragile conditions. The end of that answer will be sad because the conversation was real. One final detail makes the overlap sharper. Voyager's remaining mission is not protected by any single heroic component. The RTGs alone cannot save it. The transmitter alone cannot save it. The high-gain antenna alone cannot save it. DSS-43 alone cannot save it. The old computers alone cannot save it. Any one of them can become the limiting factor, but none of them can carry the mission by itself. That is what makes the final years delicate. The mission is strong only as a relationship among weak margins. A little power saved here, a little pointing recovered there, a slower data rate, a restored transmitter, a careful command, a scheduled dish, a reply that arrives late but clear enough. This is also why Voyager remains scientifically and culturally powerful without myth. It is not powerful because it will travel forever in a poetic sense. It is powerful because a real machine, built with finite parts, is still inside a disciplined conversation with Earth after nearly half a century. The achievement is not vague wonder, it is the continued closure of a link budget against time, distance, aging, and declining power. When that link no longer closes, the mission's meaning will not disappear. It will become historical, the data will remain, the engineering lessons will remain, the spacecraft will remain. But the active question and answer relationship will be over. That is the boundary we have been approaching from the first sentence. So the honest answer is not a single final day. Voyager can keep talking while enough of the operating stack still overlaps. Power, pointing, transmitter function, onboard computers, fault protection, command timing, and the deep space network on Earth. Science may fade first. Engineering data may continue longer. A carrier might be detectable after normal science return is gone. Commandability could become the real boundary before every radio trace disappears. And through all of that, the spacecraft itself keeps moving. That is the distinction we needed from the start. A mission is not just an object in space. It is an object still connected to meaning, command, and reply. Voyager's body can continue through the dark for ages after the mission conversation has ended. The silence is not the spacecraft stopping. The silence is Earth no longer receiving a useful answer. Now the opening image is different. A small old spacecraft keeps its antenna aimed home. A dish on Earth waits. Between them is distance, delay, weak radio, shrinking power, aging hardware, and a chain of decisions that has to keep holding together. There may be science into the 2030s if health and power allow it. There may be engineering contact beyond the end of science. NASA's FAQ language allows for DSN contact through about 2036, depending on the remaining power to transmit. But none of that is a clean promise. It is a conditional window built from margins, and that is more interesting than a countdown, because the real ending is not a last message written for us. It is the moment a recovery no longer works, or a transmitter no longer carries meaning, or the antenna no longer points, or the power ledger can no longer support the systems that make a reply possible. When that happens, Voyager will not become less real. It will become unreachable. The spacecraft does not have to stop for the mission to end. It only has to stop answering. That is why we should not rush past the quietness of the ending. The last useful answer may be a few numbers, a confirmed state, a faint carrier, or nothing that can be trusted. But by then the shape of the loss will be clear. It will not be the universe taking Voyager away. It will be the closing of a link that depended on power, aim, timing, memory, radio, and patient listening from Earth. That is the boundary. By the end of this journey, the simple phrase, "still talking," should feel different. It is not a miracle word, it is a stack word. It contains a power budget, a transmitter mode, an antenna direction, an old computer, a command path, a ground network, and a delay that turns every answer into yesterday's news. That stack has held for longer than almost anyone had any right to expect. It has held through weaker power, lost instruments, old memories, delayed commands, and recoveries that had to be built one cautious step at a time. Its ending will be quiet because the achievement itself has been quiet. One narrow reply after another, crossing the dark while the margins shrink. And once that boundary closes, the next question belongs to a different story. The silent object will keep traveling, but this conversation will be over. Tonight, we were not asking where Voyager goes after Earth stops hearing it. We were asking what keeps the answer alive until then.